from the beginning. Okay, hello students and welcome to Friday Math Happy Hour. Today's topics are going to be solving exponential and logarithmic equations. Okay, so let's begin with, here are the topics covered for today. We're going to do like a little review of what I did last week, just like the first 2 or 3 minutes, which are writing logarithmic equations into exponential equations, writing exponential equations into logarithmic equations, and also we're going to be expanding and condensing logarithms by using the properties. And then comes the solving exponential equations by using the same base rule, solving exponential equations with different bases, and finally solving logarithmic equations by using logarithm properties. Writing exponential equations to logarithmic equations and vice versa. This is what we covered last week, so I'm going to do a quick review because this is very important. Okay, definition of logarithms to base day. Y equals to log of base day of x means a to the y equals x. This is a logarithmic form. This is exponential form. Okay, example number 1. Write each logarithmic equation into an exponential equation. Okay, so here guys, we have to know what the a is, what the x is, and what the y is. Right, so it's got to go from logarithmic into exponential. So we have to know what the a, x, and y is. If you notice, the a or the base is going to be 9. I believe some books use a as a base and some others use b as a base. It doesn't matter, but this little small letter there, that's a base. And the x is going to be 81, and the y is going to be 2. So then you have to know what the a, y, and x is to put it from logarithmic into exponential. You see, so my a is 9, right? My a was 9, my y was 2, or is 2, and my x is 81. So you go from logarithmic to exponential. Now let's go the other way around. Like I said, this is like a quick review of last week. Write exponential into logarithmic form. So again, you have to know what the a, what the y, and what the x is, right? So we have to go from exponential into logarithmic form. So you notice my a is 5, correct? And my y is going to be 3. And my x is 125. So then this becomes 3 equals to log of base 5 of 125, right? Because my y is 3, right? We have it here at the bottom. My base is 5, the a is 5, and my x is 125. Or it can be written the other way around. Log of base 5 of 125 equals 3. So these two are the same thing. Okay, now, in order to graph without a calculator, you must convert logarithmic equations into an exponential equation. Okay, and again, this is a review from last week. I'm going to graph one exponential equation and one logarithmic equation, and then we'll start with the topics for this week. Examples of exponential functions, right? All these are exponential functions, right? If you notice, the exponent is a variable. It can be an x, it can be a y, but most of the times they use an x as the exponent. You see, they all have an x, right? Okay, recall this is also a property that's going to come in handy on today's lesson or today's workshop. A is a base. The exponent is a variable letter frequently x. I mean, right? Like here, the exponent. For example, f of x equals to a to the x. It has to be more than 0. Now we're going to graph, right? We're going to graph f of x equals to 2x. Like I tell my students that you always use the x equals to -2, -1, 0, 1, 2, and 3. Those will be the points or the values for x that you're going to plug in to find the point, which is the x and the y. Okay, so let's draw a little table here. These are my x values and these are my y values, right? F of x is the same thing as y. So here we're going to put f of x, which is the values for y. Okay, let's do our table. So I'm going to plug in -2. So if we plug in -2 for x, we're going to evaluate it at f of -2, right? We're going to plug in -2 for the x's. And these properties, I believe we learned them about 3 weeks ago. if you have a negative exponent, you make it positive by putting 1 over it, and then you simplify. So when x is negative 2, f of x or y is 1/4. So you're going to go there. Now let's try negative 1. And we repeat the process. So f of negative 1 means that I'm going to plug in negative 1 where the x is here at the original function. Now we evaluate. So it's going to give us 1/2. So when x is negative 1, y will be 1/2. Okay. Now let's try 0, f of 0. Anything to the 0 power will be 1. It doesn't matter what it is. So 2 to the 0 power is equal to 1. And that's an important rule that you guys need to know. Right? So when x is 0, y is 1. Now let's try 1 for x. So let's find f of 1, which again we plug in 1 where the x is on the original function. So it's going to be 2 because 2 to the first power is 2. So when x is 1, y is 2. Now let's find when x is 2. We're going to solve for, evaluate f of 2. And again, we plug in 2 for the x on the original function. So we get 4 because 2 squared is equal to 4. So when x is 2, f of x or y is 4. Now let's try 3. So we're going to evaluate at f of 3, which means I'm going to plug in 3 to the original function again. So 2 to the third power is going to give us 8. So when x is 3, y is 8. And there's my graph. If you notice, guys, again, this is from last week. If when x is negative 2, right, negative 2 will be right here, right? Which means it's going to be 1/4. So that means that here the unit of 1, we're going to cut it into 4 equal parts. So when x is negative 2, y will be about right there, about 1/4. And then when x is negative 1, it's going to be 1/2. And when x is 0, y is 1. The point is here. And then when x is 2, y is 4. The point is right there. And finally, when x is 3, y will be 8. You see, guys, that's why these points are the ones that are usually used, because if we plug in 4, right, 4 for x, it's going to give us 16, and it's going to be way out here on top of the graph, right? It's going to be out of range. So that's why these are the most common points to use, most common values for x to use, okay? Now, let's graph a logarithmic function. And here's where we have to apply the property, right? That we have to convert the logarithmic function into exponential function. Okay? So example 4, graph y equals to log a base 2 of x. Okay? So that means this, right? How I started today's lesson, right? We have to convert it to exponential. So my a is 2, my y is just like y, and the x is x, right? So now, instead of plugging in values for x, we're going to plug in for y. Why? Because it's much easier to plug in for y. If we plug in for x, we can still find the value for y, but it's going to be a little bit more challenging. So that's why it's always wise to plug it in where the exponent is. This way, it will be easier to evaluate it. So if we do the same thing, guys, right? If we plug in negative 2 for y, it's going to give us 1/4. Negative 1 for y is going to give us 1/2, and so forth, right? So these are very similar to the one that we did earlier, but the one that we did earlier, we plug in the values for x, and we got the same values for y. Okay. So again, all these values I plug in for y, and that's why x is what it is here. Now, this graph, right? This is the one that we graphed earlier, right? The blue is the exponential. Now for the right, it was y equals to the x, the one that we did earlier. And this is the log, right? So this one, and let me go back real quick. This one here, right? We converted into exponential, and here it is. It's this one here. Check this out, guys. When x is 1/4, right? X is 1/4, it's going to be about right here. X is 1/4, y is negative 2. It's right about there. And then when x is 1/2, 1/2 will be right there. The y value will be negative 1. It's right there at that point. And then it's going to be 1, 0. And then when it's 2, it's going to be 1. And then when it's 4, the y value is 2. And then when x is 8, the y value is 3. And it keeps going like that forever and ever. kind of direction. So in other words, these are inverses of each other. Okay. And again, I don't want to go too much into inverses because that's another topic. So this is a recap of what we learned last week. And I did it again because it's very important for you guys to know how to graph exponential functions and logarithmic functions. Okay, now comes expanding or condensing logarithmic expressions. I believe the word that they use in the 1324 book is expanding or putting in or writing in a single log. That's what it means by condensing or condense. These are the properties that you guys should know, right? This is called the product property, the quotient property, and the power property. For example, this is called condense, right, or single log. I'm here on the left side, and these are called expanded. If you notice, when you have log a base day of x and y, we separate them with a plus, right? And then, but we do each one individually, log a base day of x plus log a base day of y. And then when you're dividing, right, when you have the quotient, like log a base day of x over y, is going to be subtraction. But you write them like log a base day of x minus log a base day of y. And this is called the power rule, or the power property. This property, guys, the exponent, when you're expanding, there's no exponents when it's expanded. So the exponent, if you notice, it goes to the front, which is r log a base day of x. These are properties that you need to know. Okay, and also the logs and the natural logs are the same thing. I mean, not the same thing, but you use the same properties. You see, guys, same thing, or I believe, same properties. So the ln of xy is equal to the ln of x plus the ln of y, and so forth. Just the same or similar to the properties for the logs. Now, it says here, write each expression as a sum or difference of logarithms without variables to the first degree. This is example number 5. So this is in a single log. I want to put it in expanded format. Okay. So you notice, guys, here which properties are present. We know, right? We know it's property number 1, right? Because here we're multiplying, and also number 3. This one here, the power property, because we have exponents. So product and power properties. So this is what I tell my students. You need to add 3 separate log terms, right? Why? Because here we have a 1, like one coefficient, one different variable, and here we have another different variable. So we're going to divide this into 3 different logs. There's log of 5, right? And since multiplication is going to be plus log of x to the 4th plus log of y cubed. Okay, now here we have to apply the power property. X cubed power property, right? The exponent must go to the front. So the exponent goes to the front. The exponent for the log of y goes to the front. Okay. Now, if you notice here, guys, there's no log here, right? There's no log. If there's no log, it's base 10. If I would have put a 10 here, like a little base, it would have still been right. But like when you do math, right? For example, if you have x, isn't it the same thing as 1x? But you don't write 1x. You just put x. It's the same thing here. If there's no base here, we know it's base 10, or we should know it's base 10. Okay. Okay, now again, let's do another example here. Now this one, right? So which properties are present on this one? If we notice for this one here, we're gonna have the, let's see here. Hey guys, if you have any questions as I go along, maybe you can actually raise your hand up or just get in the mic and tell me what it is, and I can give you clarification. Because even though I'm showing my screen with a PowerPoint, I have another computer where I can see if somebody put something in the chat or something. So on this one here, right, it's going to be, if you notice, which properties are present. We have the product property, we have the quotient property, and we have the power property. So all 3 will be present on this one. Okay. So how should we do it then? Okay, check this out, guys. So first, let's execute the quotient property. So this is right. So this is like property number 1 here. So it's going to be log, right? Log of a of x, which is, this is my numerator, which would be this one here. And then minus, right, because it's a quotient, minus the log of w. Now this one, guys, this one needs to be expanded also here. Okay? So then we execute the product property on the log of x of y squared. So it becomes log of x, right, plus log of y squared minus log of w. But now the power property must be executed. So for the power property, right, the exponent, here on the rule here, must go to the front. Goes to the front. That's your expression simplified. Now let's try one more here. Again, here are my properties. Write this expression as a single log. Now you have to go the other way, right? It's going to be condensed. It's going to be expanded. You have to condense it in a single log. Okay. So so right away we know is right is minus, right? So minus means we're going to have to apply the quotient rule. Power and quotient, right? Because here we have this is this here, like the R here, guys. That's your exponent, right? So this is also the exponent rule. So the first thing that I do, execute the property coefficient in front, right? This coefficient must go to as an exponent, right? Because now we're going backwards. And then the minus, right? The ln of x plus 3. Now we can execute the quotient rule, right? We subtract, right? Because the quotient rule is subtraction. So that's my answer, guys. If you notice here on the quotient rule here on top, the numerator goes first, the denominator goes second. But if you go in the other way around, the first log, the variable for the first log will be your numerator, and the second variable on the log will be your denominator. Here, guys, these are binomials, so the first binomial goes on top as a numerator, and the second binomial for the ln of x plus 3 goes on the bottom. So this is your simplified expression. Okay. Now comes the solving portion of this of this workshop here. Here, to solve exponential equations without a calculator, you need to know previous topics such as. So this is what you gotta know, guys, from previous from earlier in the semester, or maybe from even a lower remedial class. You will know perfect squares. What are perfect squares? These are perfect squares because 2 squared equals to 4, 3 squared equals to 9. So you have to know these right here. At least know all the way to 10, right? 10 squared will be 100. These are the perfect cubes that you must know. Like h is a perfect cube because 2 cubed is 8, 3 cubed is 27, and so forth. So these know at least all the way to 6. Okay, so what else do we need to know? Also the fourth roots. For the fourth roots, at least know all the way to the 5. 5 to the fourth 5, which is 625. Okay, let's see what else we need to know. We need to know exponential expressions. A to the m, right? A is called the base, m is the exponent. You have to know that also. You also have to know the exponent power rule, right? The exponent power rule. So if you have a power to a power, right? We multiply the powers. You see here we have a to the m to the nth power. We multiply the powers. So that's also crucial for solving exponential equations. And finally, you need to know how to solve one variable equations. Just simple, like example, you need to know how to solve something like this. Okay, to be able to understand how to solve exponential equations. So with that said and done, let's begin. Okay, so this here is like your first rule here. This is your first rule, okay? It says let a be a positive real number with a cannot equal to 1. So if you have the base a to the u power equals to the base a to the v power, then u must equal v, right? For this to be true. Okay, let's do an example. Example A. if you have 3 to the x equals 3 to the fifth power, right? By applying the rule, right, we have the same basis here, same base, right? So then the exponent must equal to each other. Okay, this is an example of what's to come. But not every time you're gonna have the same base. So you're gonna have to make them equal to the same base by using some of the perfect squares and perfect cubes and stuff that I showed you in the previous slide. Example number 9. If we notice, right, before we can apply the rule, this rule here, right, the bases must be the same, right? So we have 8 and 2, not the same base. So then we have to make it the same base. And we notice from the previous slide, right, 8 is equal to 2 cubed. So then I'm going to substitute 2 cubed for the place of the 8. There, and then I bring down the exponent equals to the fifth. Now I'm going to apply the power rule, right? When you have a power to a base raised to a power to another power, we multiply the powers. You see, so 3 times x is 3x. Now we have the same base. So now we can apply the rule. When you have the same base, the exponents must equal to each other. So 3x equals 5. Now I solve for x. We divide both sides by 3. And we get x equals to 5 over 3. So that's my answer for this one here. And you can go check this out. You can always check your work. How can we check it? Is by going back to the original example. The example 9 here, we have 8 to the x equals 2 to the fifth. So we know that x equals to 5/3, right? Because that was the answer that I got. So we're going to plug in 5/3 for the x and see if it gives us what's on the left side, on the right side. And we notice, guys, we can, like it says here, we can plug into a calculator, or we can do it without a calculator. So we know that 8 to the 5/3 power is equal to 32, and 2 to the fifth power is equal to 32. But how do we do it without a calculator? Okay, we apply the fractional exponent rule, which is crucial for this section here also. Okay, if you notice, we have 8 to the 5/3. Here we have 8 to the mn. If you notice, the 8 is your base, right? So that's going to go inside the radicand, right? That's my radicand here. That's my 8. The numerator, the 5, right, is like the m here. Is going to be the exponent over here with a radicand. And the denominator on the exponential function is your index. You see, so this is my denominator, the n, that's your index. So then we have the cube root of 8, right, raised to the fifth power. So now you can evaluate the cube root of 8 is equal to 2. Why 2? Because this means one number multiplied by itself 3 times will give you 8, so it's 2. And then the 5 just comes down. And then 2 to the fifth power will equal 32. Because 2 times 2 times 2 times 2 times 2 5 times will be 32. This is how you do it without using a calculator, which I highly recommend. Okay, but in this course, I believe the calculator is you can use a calculator, so you can use that to verify your answer. Okay, but many instructors require work, and so do I. So you have to show me the work, and you can use your calculator to actually check your work. Okay, let's do another one here. Example 10. We have 9 to the x power equals 27. If you notice, the rule cannot be executed because these are not the same base. Now, if we go 9 squared, right, 9 squared equals 81. If we notice, it's 9 equals 27, so that means that I have to get similar bases for both 9 and 27. So let's see what happens here. Okay, find the common basis between 9 and 27. So I know 9 is equal to 3 squared, right? And I know 27 is equal to 3 to the third power. So then I'm going to substitute 3 squared for 9, and the x comes down. And I'm going to substitute 3 cubed for 27, right? Then I must apply the power rule here. Apply the exponent power rule, which means when you have a power to a power, you multiply the powers. So this becomes 3 to the 2x because 2 times x is 2x equals to 3 cubed. Now we have the same basis, right? We had the base of 3 and 3. Now we can apply the rule, which means when you have the same basis, you let the exponents equal to each other. Now here, to solve for x, we divide both sides by 2, by 2. So divide by 2, so x equals to 3 over 2. And similar as before, you can always check your solution. Okay, so let's check it. X equals to 3 halves, so x equals to 3 halves. Right, so we know that if we plug into the calculator, it's going to give us 27. Right, so we know that's a solution. Are you guys okay up to this point? You guys have any questions that you can put in the chat if you want? So no questions, so I can continue then. Okay, I repeat, guys, if you want me to clarify anything that I've gone so far, please stop me right there and then when you need clarification, because it's kind of hard to go back to the previous slides because I have a lot of animation. Okay, so please feel free to just put something in the chat. That way I can stop and clarify things for you. Now there's one more. You see, they keep getting a little bit more challenging and challenging every time. Again, at the same base. 4 squared is 16. It's not 32, right? So let's do 4 cubed. 4 cubed is 64, right? Not 32. So that means both bases, I need to find the common base for 4 and 32. I know that 4 is equal to 2 squared. And I know 32 is equal to 2 to the 5th power. So as before, I'm going to substitute 2 squared for 4. And then we just bring down the x minus 1. And I'm going to substitute 2 to the 5th power for 32. Then I need to apply here, guys, right? I mean, the power rule here. I need to apply the exponent power rule. Which means, right, when we have a base raised to a power raised to another power, we multiply the power. So this will be 2 times x minus 1 equals to 2 to the 5th. Now here, guys, right, now we have the same base now, right? Same base. So same base, now I can apply the rule. So we have 2x minus 1 equals to 5 because when we have the same basis, we let the exponents equal to each other. Now here I need to distribute. So 2 times x will be 2x. 2 times negative 1 will give me negative 2. Now we're going to add 2 to both sides. Right, so if we add 2 here, there'll be 0. If we add 2 here, it'll be 7. Now we divide by 2. So x equals 7 over 2. And as before, we can always check our work. So x equals to 7 over 2. So we have 4, right? So I'm going to plug in 7 over 2 for the x's. So 7 over 2 will give us 5 over 2, right? Because if we find the same common denominator, right? 1 is the same thing as 2 over 2. So we have 7 over 2 minus 2 over 2. 7 minus 2 will give us 5. That's why 7 halves minus 2 will give us 5 over 2. And again, if you put that in the calculator, it's going to give us 32. So this actually checks out. Okay. Now, to solve logarithmic and exponential equations, we need to know previous properties such as the ones from before. Okay. So these are properties that we must know. So example. Okay, now guys, recall example 10 when we had 9 to the x power equals 27, and I told you that we have to have the same basis, right? So now there's another way to get the answer. Okay, let me show you how. Recall the answer was 3 over 2. If we go back, I think like 3 slides back, this was the answer for this problem here. For example 10 from a few slides back. How can we solve it using another way? We can solve it using the power property of the natural logarithm. So here, guys, we're going to use this rule here. Okay, how does it work? We're going to take, right, because we want to bring the exponent, we want to bring it down. So how we bring it down is we're going to apply the ln to both sides, and the exponent comes to the front. Okay, we need to bring down by taking the ln of both sides. So my ln there, and there's my ln. Now, guys, if you take the ln here to the left, you also have to take it to the left here, because it doesn't make sense if you put the ln on the right. So if it's on the left of the right side, of the left side, then it also has to be on the left of the right side, for example, of the number here. So then by rule, right, the exponent comes to the front. So this becomes x ln of 9 equals to ln of 27. Then we divide both sides by the ln of 9. And then what we do is put it in the calculator. And that's my answer. 1.5, which is equal to 3 halves. Okay, now, hey guys, this is very important. Okay, at times when students don't have a good, when they don't have like a good, foundation with logs, and also with the ln, with the natural logs, they tend to, here, they tend to divide 27 and leave the ln by itself there, and vice versa here with the 9. Hey guys, the ln of a number is actually a value. This here together, guys, this together, the ln of 9 is a number. It goes together. You cannot separate them. So please, guys, be real careful with that. This is very important, and I see a lot of students make those mistakes. It's very important. Like I put here, the ln of a number is actual value. Cannot separate them. Okay. Okay. Now let's apply another rule. It says that u and r are real numbers with u positive, then the ln of u to the r power equals to r ln of u, right? The exponent comes to the front. Example number 12. So this is the rule that we're going to be applying, okay? So we have the 5 to the x equals to 8. It's because at times there's no way that you can find the same base. For example, 5 and 8 do not share the same base. So that's why it's impossible to do it by using the same base. So that's why there has to be an alternative. And the alternative is how I did the previous example. Okay? Not the same base. And I cannot get them with the same base, right? That's what I mentioned right now. So you have to bring down the exponent by taking the ln of both sides. So what we do, guys, we're going to take the ln of both sides. The ln of the left side and also of the right side. Now, by rule, the exponent goes to the front. Then, remember what I was saying, that the ln of 5 is an actual value. You cannot separate them, they go together. So I'm going to divide both sides by the ln of 5. And then all you do is use your calculator. So, in my math lab, and also on your textbook, it always states to round off to say 4 places or even 6 places, but most of the times it's 4 places. I believe I saw today in my NCBN class that it said to round off to 6 places. Okay, and that what it means with those squiggly lines. It means that it's being rounded off. So the answer will be 1.2920. Okay, now how can we check it? We plug the original. We plug in the value, right? This value here, 1.2920, into the original problem. Okay, we're going to plug it in for the x. So since we round it off, it's going to give you something real close, right, to 8. You see, guys, it gives me something like 7.99996. Because when we round off, it's going to be a little bit short, but not that much. Yes, Marisol, let me see. So we cannot separate into ln of 8. I don't understand what you mean by 8/5. Here, the ln, you have to put ln of 8 divided by ln of 5, Marisol. If you have a calculator with you, it's supposed to be something like this. Okay, let me put it in the chat. It's supposed to be ln of 8 divided by ln of 5. That's the way it's supposed to be entered into the calculator. For example, what you did here, the ln of 8 divided by 5 is not correct. It has to be the ln of 8 divided by ln of 5. Marisol, did that make sense? Oh, that's you. Thank you, Patricia. Like Ms. Patricia said, you can use parentheses for top and bottom. Okay, that's another way to maybe to clarify. I mean, some of the problems at times. But Marisol, are you okay with that? Oh, so you were talking of the quotient rule. Okay, if you have, let me go back. If you have the ln of 8 over 8 divided by 5, let me see here. But using the quotient rule is going to be the ln of 8 minus the ln of 5. So what you have here, Marisol, is going to be this right here. The ln of 5, the ln of, okay, check this out. When you just put right there, you said the ln, let me put here the ln on the chat. The ln of 8, let me see here, of 8 divided by 5, right? That's equal to the ln of 8 minus the ln of 5. Okay, let me put it here on the chat here real quick. You see the ln of 8 divided by 5 equals to ln of 8 minus ln of 5. Okay. Marisol, are you okay then? Can I move on? Okay. Okay, that's good that you understand it. Okay? Hey guys, keep asking questions. It doesn't matter, okay? We got time. Now I believe this is going to be, I think, my last one here. I think I have one more example, or maybe even two. This way I can answer any questions that you might have, or also the tutors can also, also help you. So again, this is another rule here. It says, let u, v, and a be positive real numbers, where they cannot equal to 1. So here's the rule here. If log of base a of u equals to log of base a of v, then u must equal v. In other words, if you have the same base here, like log of a on both sides, log of a, right? Then these values must equal to each other. That's what this rule is saying here. Okay, example. I should have used easier example. Okay, but anyway, let me show you this one here. If you have log of x equals to log of x plus 3 minus log of x minus 1, before you apply the rule here, guys, there has to be a single log on both sides. Okay? To apply the rule, a single log must be on both sides. So then here we're going to use the quotient property, right? So I'm gonna transform the right side, the log of x plus 3 minus log of x minus 1. I'm going to write it as a single log, right? We call the rule, when you have a minus, right? It becomes division. So the first here binomial is your numerator, and the second binomial becomes your denominator. For the logs. Now I need to solve it. So to solve it, right? When you have the same base, right? We have log of base 10 of x equals to log of base 10 of x plus 3 divided by x minus 1. Remember, guys, when there's no base, it's base 10. So then we apply the rule. So we have x equals to x plus 3 divided by x minus 1. Now here, you can do it like two different ways. You can multiply everything by x minus 1 to cancel the denominator, or you can cross multiply. I believe here I cross multiply, right? Because there's like a 1 here on the bottom. So it will be x times x minus 1 must equal to 1 times x plus 3. Now I'm going to distribute. X times x will give you x squared. X times negative 1 will give you negative x, right? Now, since we're solving, I have to let it equal to 0, so the terms on the right side must go to the left side. Right, so equation equal to 0. So I'm going to subtract negative x and minus 3 to both sides, right? Because x minus x will give you a 0, and 3 minus 0 will also give me a 0 on the right side. But here we have x squared. negative x minus x will give you negative 2x, and we bring down the negative 3. Now I need to factor. Okay, I need to factor. So I believe I went over, on week 3, I went over the factoring workshop. If you guys don't know how to factor, please try to get some help because it's crucial to know how to factor. Or you can go back to the recording, week 3, and it shows you, and I explain how to factor. Or if not, you can go to tutoring, or come to my Sunday numbers. It doesn't matter what you do, but please try to know how to understand factoring. So we said binomials equal to 0. So x minus 3 equals 0, or x plus 1 equals 0. So then it's going to give us, right? We saw for x, it's going to give us x equals to 3, or x equals to negative 1. So these are my solutions, right? So, but let's check them. We got to check them. So to check them, right? If you guys have access right now to a calculator, in your calculator, enter log to a negative number, to like a negative 1, negative 2. And if you do that, it's going to give you error or not a real solution, which means that the logs cannot be negative, nor they can also be 0. If you plug in, if you put in the calculator log of 0, it's going to say also the same thing. It's going to say error or not a real number, which means that the logs must always be more than 0, positive. Okay, so right away I know that negative 1 cannot be the answer. Okay, because if we plug it in, right here, this is not defined. That's why I know it cannot be a negative answer. So the negative 1 is not a solution. Okay, now let's plug in 3. More likely that 3 is going to work. Right, so we're going to plug in 3 for every x. Right, we plug in 3 there, 3 there, and 3 there. Now, right, this is 6, right? 3 plus 3 is 6. Now here, we can use a calculator, right? So this will be my answer. But we can apply what we learned, the rules that we learned so far. Okay, this is the answer, right? So it's true. 3 is the answer. But we can do it without a calculator. Check this out. The left side is log of 3, right? Log of base 10 of 3. So then on the right side, we're going to apply the quotient property here. Because we have subtraction, it's going to be the quotient rule. Right, with the quotient rule, right, it's going to be divided, right? If it's minus, and we put it in a single log, it's going to be division. What's 6 divided by 2 is going to give us 3, right? So we know this is correct. That's my solution. Now we have one more, I believe. Example number 14. If you have log of base 3 of the binomial 6x minus 2, right, equals 2. Here, right, we're going to apply the rule here. Let me explain the rule first. If a and u are positive real numbers with a cannot equal to 1, then this rule holds. If you have a right base a to the power of log of base a of u, right, the base a and the log of a, that becomes 1. So whatever is here is your answer. Okay, so let me show you what I'm talking about here. Right, we need to cancel the log of base 3. How do we do it? Is we're going to put a big 3. Right? Here's what I mean. We let the expression on both sides of the equal sign, right? These expressions become be the exponents, and the base of the logarithm be your base. So in other words, all these are going to be your exponents, right? But the base here is going to be your base down here. So in other words, whatever base it is, you're going to put a 3, and this becomes my exponent. What I do to the left side, I must also do to the right side. Now, by applying the rule here, 3 log of 3 of 6x minus 2, right? This will equal to 1. So all we do is bring down the 6x, the 6x minus 2 equals to 3 squared. And all we do is just simplify. So 3 squared is 9, and then we solve for x. We add 2 to both sides, right? And we add 2 to both sides. It's going to give us 6x equals to 11. We divide both sides by 6. And the answer will be 11 over 6. Okay? And again, we can always check our solutions. It's always wise to check your solutions. Here, I'm going to go to the original problem, okay? Right, there was this one from the beginning. So I'm going to plug in 11 over 6, right, for the x. Right, there was my solution, so I'm going to plug it in right there for the x's. So 6 times 11 over 6, right, the 6, and 6 divided by 6, this will cancel here, that'll be equal to 1. So I'll be left with 11 minus 2 inside the log. 11 minus 2, right, will give us log of base 3 of 9. Now log of base 3 of 9 is going to give us 2. By you apply the change of base, or you can do this, guys. Isn't 9 the same thing as 3 squared? So this becomes 3 squared, and the exponent goes to the top. And log of 3 of 3 is equal to 1. You can do it like, I think, like 2 or 3 different ways. You can also use the change of base. So anyway, that's the solution, guys. Hey students, do you have any questions on anything that I just went over? So let me end my show and let me get back to let me get back here to the main page here, to the home page.
Is there any more questions for Mr. Azasi?
Let me see, Brenda, okay? Example 13. Let me see here real quick. I need to share my screen again, okay? So let's go to, you said example 13? Let me see here in the chat. Okay, let me go back there, okay? Let me again share my screen real quick. Let me share my screen again. And you said example 13. Okay. So I need to find it here. Let me go here. I need to go and get it. Let me go here real quick. Sassy. Let me go here. Let me go workshops. Let me go here. Let me go here. And here. And here we go, right? You said example 13. So let me go straight to that example. Let me see here. Example 13. Let me see here. Is that it? No, example 11. Example. Here we go. This one here. Is that the one? Let me see the chat here. Is this the one that you were asking?
Yeah, it is. I just didn't get the last part.
Okay. So let me start the slideshow at this from the current slide. Okay. So here we go. Let me know what part you don't get. Okay. Here are the rules that we're trying to do. I mean, in order to apply this rule, you're gonna have to have a single log on both sides, right? For example, the left side is okay, but the right side is not okay, right? Because here we have 2 logs. I have to this one I have to condense it or write it as a single log. So we're going to apply the single log must be on both sides, right? So we're going to use the quotient rule. You recall the quotient rule, right? The quotient rule, if it's a fraction, that means that these will be division. Okay. Now we have the same base, right? Once you have the same log of the same log on both sides. For example, we have log of base 10 on both sides, log of base 10, log of base 10. So then we let the logs here, like u must equal to v. So it's going to be x equals to x plus 3 divided by x minus 1. Okay. Now here I cross multiply. Okay, that's what I did. But you can do it another way, is by actually multiplying both sides by x minus 1. Why? Because I don't want this to be a fraction here, like a fraction expression. So I want to cancel the x minus 1. How do we do that? Is by multiplying both sides by x minus 1. So if I multiply x minus 1 here on the right side, I'm going to be left with x plus 3. And then, but I have to multiply x minus 1 to both sides. So x minus 1 times x is right here on the left side. And x minus 1 times x plus 3 over x minus 1 the x minus 1 will cancel. Are you with me up to this point?
Yes.
Okay, now. So now here I'm going to distribute. Right? So x times x will give me x squared, and x times -1 will give me negative x. So then when you have, this is like a quadratic, right? Because we have a power of 2 there. So then we have to let it equal to 0. Right? Set the equation equal to 0. That means that all the terms on the right side must go to the left. So I'm going to subtract x to both sides and subtract 3 to both sides. Right? So then here on the right side, it's going to be 0, right? Because x minus x will give me 0, and 3 minus 3 will give me 0. But on the left side, these two terms, right, we can combine them because they're both the same or like terms. So negative x minus x will give me negative 2x. And then the x squared just comes down because there's no other like terms, and the negative 3 comes down. Do you follow up to this point?
Yeah.
Okay, now we got a factor. So to factor, like I mentioned earlier, that I presented in a workshop on the 3rd week on how to factor. So this trinomial becomes the factor in the factor form becomes x minus 3 and x plus 1. Are you with me up to this point?
Yes.
Okay, now if you still need help with factoring, you can join the tutor, so you can join my Sunday numbers, or go back and watch the video. The recording for week 3 on factoring, and maybe that can give you like more insight on how to factor. Okay. So then here we apply, it's called the zero property theorem, which means we're going to set both binomials equal to 0. So x minus 3 is equal to 0, and x plus 1 equal to 0. So here we're going to add 3 to both sides. So it's going to give us, okay, let me see here. It's going to give us, let me see what I do here. Oh, here we go. We're going to solve for x, right? So here I'm going to add 3 to both sides. So it's going to give me x equals 3. And here on the right side, I'm going to subtract 1 to both sides. So it's going to give me x equals to -1. So these are my solutions up to this point. Can I proceed? Are you okay with this?
Yes.
Okay, now I'm going to go on the next slide, okay? So I'm going to check my solutions. So let's check them both, right? This was my original problem here. Log of x equals to log of x plus 3 minus log of x minus 1. So first, I'm going to start off by plugging in x equals to -1 on every x here. Right, so I'm going to plug it in there, and there, and in there. If you notice, if you have a calculator with you, enter log of a negative number. And you're going to find out of a -1 or any negative number, you're going to find out there's going to be undefined, or it's going to say error on your calculator, or it's going to say not a real number, which means that logarithmics cannot be negative, nor 0. They have to be positive. Okay? So not defined. So that means that x equals -1 is not a solution to this original problem here. Then if we test the 3 out, right, then I'm going to plug in 3 for every x. You see, I'm going to plug it in there for the log of x. I'm going to plug in 3 there for the x. And the x plus 3, I'm going to plug in 3. And also for the x minus 1, I'm going to plug in 3 for the x. So this becomes log of 3. This becomes 3 plus 3 is equal to 6. And 3 minus 1 is equal to 2. Now you can actually put this in the calculator because these are both base 10. So you put log of 3 in the calculator, it's going to give you something like 0.4771, right? And you put log of 6 minus log of 2 is going to give you the same thing, 0.4771. But like I mentioned earlier, you can do it without a calculator, right? So I'm going to be applying the rule that we just learned. This is called this is the quotient rule expanded. So I'm going to condense it or put it as a single log, right? Use the quotient property. So the quotient property, right, as a single log is going to be your first, the log of the first value here is your numerator, and the log of the second value here becomes your denominator. So 6 divided by 2 will give us 3. And if you notice, they're both equal to each other. Did that make a lot more sense?
Yeah, it did. It was just, I just had to go slower with it.
Okay. It's because I have to go like at a steady pace because we only have like an hour of the workshop. But I don't mind answering your questions. And you should never feel embarrassed asking questions also in class. You always get clarification before you leave the classroom. Okay, so are you okay? Are you satisfied with the way I explained the material?
Yes.
Okay, thank you very much. So let me go back to the home page here. And that way, let me stop sharing my screen here. Okay. So now we're back. Okay. Ms. Medina, are you okay?
Yes.
Okay, thank you. Thank you. So I guess that's it, guys, okay? Thank you, Patricia, for your patience, and you too, Rafael. Thank you for being so patient with me.
Thank you, sir.
Thank you, Mr.
Before I let
Jackson.
you guys go, let me go ahead and I'll invite you to next week's session. Sorry, tongue-tied here. So next week at 1 o'clock, we're going to have Fitness by Jeremy Perales. And then from Happy Math Hour for Math 1314, we'll be finding zeros of polynomial functions. And for Math 1324, we'll be doing simple and compound interest annuities. I want to thank Mr. Azasi for presenting today. I would like the audience to say, I'd like to say thank you to the audience. And I hope you have a wonderful weekend. Thank you, guys. Thank you all for coming.